In this section, we're going to start discussing how to balance redox reactions. To determine which element is oxidized or which is reduced, we look at the change in an element's oxidation state. So in the previous section, we got comfortable with assigning oxidation states. Now we're going to look at how those oxidation states change. So I've assigned oxidation states for each element here. So this hydrogen with its +1 charge has an oxidation state of +1. In this IO3- ion, the oxygen as expected is -2, the iodine is +5. Here the fluoride ion is -1. Now on the product side, we have two elements that are in their standard state. So those have oxidation states of 0. And then in this water molecule, as expected, hydrogen is +1 and oxygen is -2. So I've just separated the oxidation states by commas for each of the elements in these compounds. From here, once we've assigned oxidation numbers to every element in every compound, we can determine which elements are oxidized and which are reduced by looking at the change in each element's oxidation state. So we can first notice, so let's highlight this down here, the oxidation states for hydrogen and oxygen were not changed. Hydrogen over here on the left starts at +1 and ends at +1. Similarly, oxygen starts at -2 and ends at -2. So those oxidation states were not changed, they're not oxidized, and they're not reduced. Let's look at the other two elements though. This iodine oxidation state goes from +5 to 0, and fluorine goes from -1 to 0. Oh, I think I mixed up my colors here. So fluorine is in red from -1 to 0, and iodine is in black from +5 to 0. There we go. So we have this change for the iodine, this change for the fluorine. So going from +5 to 0, that's getting more negative, right? Closer to 0. Getting more negative means gaining electrons. So I would call this gaining electrons or reduction. And then to go from -1 to 0, that's getting more positive, right? So that's losing electrons or oxidation. So summarized down here below, iodine was reduced from +5 to 0. Fluorine was oxidized from -1 to 0. When we balance redox reactions, we don't just balance the atoms like we're used to seeing in other balancing equations. We also have to balance the electrons. So let's look at this example and balance this reaction. So we have copper 2+ plus silver solid produces copper solid and silver plus. First, let's determine the oxidation states of the elements. So let's try this before we go look at the answers on the next slide. So elements in their standard state have an oxidation state of 0. So these two solids are 0. And then the ions just carry their charge. These individual monatomic single ions carry their charge as an oxidation state. So copper 2+, oxidation state of +2, silver metal 0, copper metal 0, silver ion +1. All right, so we have our oxidation states assigned. You can see them there, +2, 0, 0, +1. Let's look at what happens though. Copper goes from 2+ to 0. So it's getting more negative. Going from positive down to 0 means gaining electrons. So this is gaining electrons, which is reduction. So copper is reduced. It gains 2 electrons. Silver goes from 0 to +1, so it gets more positive. That means it lost electrons. Losing electrons is oxidation. So we see here, silver is oxidized. It loses 1 electron to go from 0 to +1. This is an unbalanced reaction because the number of electrons gained is 2 and the number of electrons lost is 1. Those need to be the same in order for this reaction to be balanced. The number of electrons gained must equal the number of electrons lost. So we have to change the coefficients to balance the electrons and also leave the elements balanced. All right, so here's how we approach this. If silver loses 1 electron only, but copper is gaining 2, we can simply double the number of silver atoms on each side in order to double the number of electrons lost. So then we can balance out not just the atoms, we've got 2 silver atoms on both sides, 1 copper on both sides, but now we also have an equal number of electrons as well. So you can see these coefficients here take care of that charge imbalance because now I have 2 + 1 ions. Okay, let's look at this following example and balance this equation for both atoms and electrons. So we have aluminum solid plus Fe2+ produces Al3+ plus Fe solid. So we'll work through the entire problem on this slide, and then I'll go forward 1 slide to show you the answer so we can check our work. So let's look at what happens to the aluminum here. Aluminum goes from 0 to +3. So it's getting more positive. That means it's losing electrons. This is losing electrons, which is oxidation. And how many electrons are we losing here? 3. Okay. Now let's look at the other element here, iron. Iron is going from +2 to 0. Okay, so going from +2 closer to 0, that's becoming more negative or gaining electrons, which is reduction. Okay, how many electrons are we gaining to go from +2 to 0? We're gaining 2 electrons. So if you look at the reaction as is, it looks balanced. 1 aluminum on both sides, 1 iron on both sides. But it's not balanced because we have unequal numbers of electrons gained and lost. So the question is, how do we get an equal number of electrons gained and lost? We have to find that common denominator between 3, or that common multiple, excuse me, between 3 and 2. So that least common multiple would be 6. So what I need to do is multiply this by 2 and this by 3 in order to get an equal number of electrons gained and lost. So we're going to multiply both aluminums by 2, so 2Al, and both irons by 3. So now this reaction is balanced for both electrons and number of atoms. So let's just go ahead 1 slide to check our work here. You can see 2 aluminum on each side, 3 iron on each side. Aluminum loses 6 electrons, and that should make sense, right? To go from 2 that are 0 to 2 that are 3+, that's 6+, right? So losing 6 electrons, and then gaining 6 to go from +6 for the iron to 0. And therefore the electrons are balanced.